Good afternoon. So today's lesson is more like a review of series testing strategies that we learned in this chapter so far. The main idea is to basically go over all the convergence tests we learned and to focus on the argument that we have to check, or the items that need to be checked in each convergence test, and more importantly, to recognize which type of convergence test can be used under certain situations. So depending on the example you have at hand. I should point out that obviously the sky's the limit in terms of how many types of series you can come up with. And sometimes you can use more than one test to prove or to check for the conversions. The way to go about this lesson, and it's very important to follow my advice so that the objective of this lesson is achieved. Make sure you print on all the convergence tests we learned. I'm gonna for those of you who are my students will have access to a handout. I'm gonna maybe post a link as well in the descriptions, because you can find on the internet plenty of sources with summaries of convergence tests. There are more than what we covered in the class, but the most the usual ones that we just covered usually are given in many sources. If you search for convergence test series in Google, you'll find plenty of examples. But it's important to have printed out that page in front of you, and it's very important to go slow and pay attention to what I write and also what I say, because sometimes some of the conditions that you need to check, you don't even have to write as much. You look at, for example, a sequence and say, okay, that goes to 0 if the limit is to be found, for instance, and you don't even need to write it down. But it's an important piece of the argument when you go over about checking to see if the series converges or not. I will also encourage you to stop the video right now and try some of these examples before you follow the video and see me analyzing each of them. In each of these series, always remember to start, at least mentally, if not on paper, with the divergence test, which states that if the sequence in the series doesn't go to 0, then the series is divergent. So if you have summation of an and an doesn't go to 0, then the series is divergent. So this is the so-called divergence test. This is very easy to check in the beginning, and if it follows, if it's applicable, then you're done essentially. You don't have to use a more sophisticated test. All right, so assuming you pause the video and you did just that, let's continue. Let's go over these examples one by one. So the first one, the summation of from 1 to infinity of n plus 1 over 3n squared plus 2. We can check mentally that n plus 1 over 3n squared plus 2 does go to 0. Remember, and you could do this mentally at this point, the limit of the type infinity over infinity using rational fractions. Remember, it's given by the ratio of the leading coefficients. So that's 1 over infinity, which is 0. So the divergence test is not applicable. We don't know whether it converges or diverges because the sequence does go to 0. It may or may not converge, but we have to use a different test. So from now on, I'm not going to write down divergence test not applicable. I'll just maybe state it if that's the case. Okay, so then we have to decide whether it's convergent or divergent. When you have quantities like this, rational fractions made of polynomials, always remember that the ratio test will fail if that's what comes to mind. It always fails, and if you don't know what I'm talking about, just go back to the previous lecture. It always fails if you have the polynomials over polynomials, or more generally, it always fails if by replacing n with n plus 1, you have essentially the same leading coefficient, leading term. That is the main reason it fails. And at this point, you are left with other tests like integral test. That doesn't look like an easy integral to do. It's kind of time consuming. It's possible, but time consuming. Then comparison test could be tricky. Limit comparison test usually works pretty much most of the time. And in the limit comparison test, and I hope you have the test in front of you, you have to pick a different series to compare with the original one. So the original series, excuse me, the comparison series, make it to contain the leading terms with respect to n. So in other words, in this case, summation of 1 over n. And if you practice long enough with this type of strategies, you already anticipate that your original series diverges. Because if the limit comparison test works, then both series converge or diverge. So again, just focus on how I go over every single argument one at a time. So I'm trying to use the limit comparison test. Then I pick this series, and then now I proceed to verify the limit comparison test by looking at the limit of the original series divided by the one I picked, divided by 1 over n. I need to simplify this a little bit. N times n plus 1 over 1 times 3n squared plus 2. Remember always to pause and go slower if you need to catch up with the computation. And now the limit is the limit of the ratio of the leading coefficients, which ends up being 1 over 3. And because 1 over 3 is a positive number, and you have to write this down like that, you have to write 1 over 3 greater than 0 to indicate to me or to the grader that you're aware of what the limit comparison test states. And it states that if the limit is positive, then both series converge or diverge. And since the summation of 1 over n is a p-series with p equals 1, which is greater than or equal to 1, then summation of 1 over n diverges. Hence, by the limit comparison test, summation of n plus 1 over 3n squared plus 2 diverges. If you're really in a rush, you can skip from n from 1 to infinity. This actually summation like n going from 1 to infinity or from 2 to infinity, that doesn't matter in terms of whether the series converges or not. Basically, it only matters if you have to compute the value of this sum if it's convergent, which in this class we can only do it for power series. In all other series we learn in this class, we don't know what the sum is anyway. We can only establish convergence or divergence. All right, so number 1 is divergent. Let's go over number 2. And let's go a little bit faster here. Notice if I check the divergence test, if I take the sequence and I take the limit, again, the limit is decided by the ratio of the leading coefficients, which is 1 over 3. Because the sequence an doesn't go to 0, then we're done. The original series is divergent by the divergence test. So always check to see if the limit goes to 0 or not, because if it doesn't, and only if it does not go to 0, one can conclude something, which is series diverges. If it goes to 0, it gives you nothing. You have to use a different test. All right, so moving on with number 3, we have n third over e to the power 2n. Again, this goes to 0, and I mean n third over e to the 2n goes to 0, so we cannot use the divergence test because the exponential goes to 0 faster. It goes to infinity faster. And now we remember that if we have at least one exponential in this series, chances are that the ratio test or the root test, depending on the case, will work. So the ratio test is usually the one to go about most of the time, except if you have maybe a power n overall, like the entire series is something to the power n, and like something in terms of n to the power n, you know, that might be easier to do it with the root test, but ratio test usually works. So the ratio test requires to establish the limit of an plus 1 over an. By an we mean the sequence in the series. And here we have to pay attention to do carefully the computation when you plug in n plus 1, when you do the substitution. When you replace n with n plus 1 everywhere, then 2n becomes 2 quantity n plus 1. And over an, it's the same as times 1 over an. So times the reciprocal of the original series. When you do the simplification, make sure you group the terms that are similar to each other. For example, write them in the same fraction, n plus 1 over n to the power 3. And then e to the 2n over e to the 2n plus 2. Then we can simplify that second term as well. E to the 2n goes away, and you're left with e squared on the bottom. Now, at this point, I'm perfectly fine if you just write the answer like that. Because you should do mentally at this point these limits, right? So n plus 1 over n goes to 1. Do this mentally because it's clearly infinity over infinity. Leading coefficients, leading terms are n and n. N over n is 1, so the limit is 1. 1 over e squared as a quantity, as a real number, is less than 1. Remember, e is 2.71 or ... So because the limit is strictly less than 1, then by the ratio test, the series is convergent. All right, so we'll continue on the second page with the next example listed here. All right, so we are at number 4, summation of 1 over n times natural log of n to the power 3. So these examples kind of scream at you about integral test. Again, it's not probably the only way to go about it. But, you know, again, the ratio test, by the way, is going to fail. Comparison test might work, but it's tricky. So who knows? And in terms of the ratio test fails, comparison test might work, but that's tricky to come up with. On the other hand, if you look at the function and clearly indicates a function that may be easy to integrate, easy is a relative term, of course, but if you look at it as a function, what's inside there in the series, so 1 over x ln of x to the power 3, this kind of looks like an integral with a u substitution, because you have ln of x and du 1 over x dx. So this looks like an integral that I can compute without too much headaches. So therefore, you should think about the integral test. So let's do the integral test, the integral from 1 to infinity of 1 over x ln of x to the power 3. So if the improper integral converges, then the original series converges, and if the integral diverges, then the series diverges. So let's do the substitution. We wrote it here already. Let's change the bounds. So if x is equal to 1, u equals ln of 1, which is 0. If x goes to infinity, u, which is ln of x, goes to infinity as well. We could do that directly, so we don't have to write the limit, right? So I mean, I'm gonna do it with the limit computed mentally later. So that's gonna be the integral from 0 to infinity, 1 over u to the power 3, and 1 over x dx is again du. The integral from I always forget about this pesky thing, because this becomes improper at 1. I had this before in a previous lecture. Let me just make a small modification here so that I don't have to write it one more time. Say this is from 2 to infinity. See, because this becomes improper at 1 as well, and I don't want to deal with this kind of complication. So let's make the integral from 2 to infinity, or the summation from 2 to infinity. So I don't have to have ln of 1, which is 0 on the bottom, and that'll be undefined or improper there. So then the lower bound is ln of 2. Okay. And everything else is the same. Sorry about that. So the integral from ln of 2 to infinity, 1 over u third, which is u to the minus 3 du, and then u to the minus 3 plus 1 over minus 3 plus 1 is the antiderivative from ln of 2 to infinity. Okay, so the first piece when you plug in infinity is actually limit as u goes to infinity. And let's write that down differently. So it's minus 1/2 u to the minus 2, which is 1 over u squared, from which you subtract minus 1/2 times ln of 2 to the power minus 2. So anyway, this is going to be 0, this first piece, and the rest of it is just a real number, like that, 1 over 2 ln of 2 squared, which is clearly a finite number, and therefore the integral is convergent. Hence, by the integral test, the series itself is convergent. All right. So moving on, example 5, summation from 1 to infinity, n factorial over e to the n squared. This is again a ratio test. If you have factorials, if you have exponentials, these work with a ratio test. The reason I put it here is just to remind people how to deal with factorials when you do the ratio test, because otherwise 5 is kind of similar to problem 3. So let's set up the ratio test. We have the limit as n goes to infinity, an plus 1 over an, and this is an. An plus 1 is going to be n plus 1 factorial over e to the n plus 1 quantity squared, divided by the same thing, by the original, which is times e to the n squared over n factorial. All right, so make sure you do the algebra carefully here. We're going to pair n plus 1 factorial with n factorial, and then e to the n squared with, and we have to expand that exponent so we can simplify it later. N plus 1 squared is n squared plus 2n plus 1. When you simplify factorial, remember the smaller factorial disappears completely, and then you write on the top the remaining factors from n, right? And in this case, it's just n plus 1. So from n, there is another factor, n plus 1, up until n plus 1 factorial. Between the next two terms, e to the n squared goes away, and you're left with e to the 2n plus 1. Once again, in this class, I'm perfectly happy to give the answer without any extra work at this point. Infinity over infinity, when you compare a polynomial with an exponential, the exponential dictates the overall limit. Exponential goes faster than any polynomial, therefore this limit is 0. If you're not convinced, you could do, for example, a L'Hopital. That's another quick way of estimating the limit. For example, if I differentiate the top, that's 1. If I differentiate the bottom, that's e to the 2n plus 1 with respect to n, right? So anyway, that's going to be 1 over infinity, which goes to 0. But at this point in your math career, I think it's practical for these limits to be known or estimated mentally and write the answer right away. Because the work is very similar in problems like this, and you should already anticipate what the answer is. We might as well write the answer without too much fuss. Now again, this is when you have these type of limits of infinity over infinity, plus or minus, let's say, but infinity over infinity, involving polynomials, logarithms, exponentials, because exponentials with the base greater than 1, for example, because knowing that exponential is that's basically the order of, to digress a little bit, the exponential essentially beats the polynomial, which beats on in turn the logarithm. So when these quantities of these types are on a ratio, you know which one dominates the other. And depending on whether that dominating part is on the top or on the bottom, then you know quickly whether the limit is 0, like in this case, or maybe infinity or minus infinity. All right, so let's see if you have room for another one here. I think we do. Actually, let's see. I don't want to be greedy on it. Let's put the next or the last two examples on the same page, because those are alternating series and I want to have them side by side. So let's stay tuned for the next page. I got a little carried over and I forgot to give the answer on the previous problem, right? So we had summation of n factorial e to the n squared over e to the n squared. And we used the ratio test and we concluded that the limit of an plus 1 over an is 0, which is less than 1. Then, of course, the series is convergent. All right, so the next one is still eligible for the ratio test. Remember, the ratio test, if it's applicable, it works for series with negative terms as well. So this is an alternating series. You could think about the alternating series test, but when you have an alternating series, see if the ratio test can be used or not. Because remember, the ratio test gives you absolute convergence as well, which of course implies convergence by the absolute convergence test. So because I have an exponential 4 to the n, then the ratio test is going to work. So let's set up again the limit of an plus 1 over an in the absolute values. See, previously I omitted the absolute values because the series were with positive terms anyway, so they didn't matter, the absolute value. But here it matters because you have negative terms in the series itself. So let's plug in n plus 1 everywhere and divided by the original, so that means times 4 to the n minus 1 to the n times n squared. The absolute value essentially kills the negative, so you could basically do it like that, but it'll be minus 1 times something, and that minus 1 will disappear when you apply the absolute value. The absolute value makes the negative disappear. And other than that, it's just like before, just group the terms that are similar together, so you could simplify them. And then 4 to the n over 4 to the n plus 1. This goes away. This fraction goes to 1, so the overall limit is 1 over 4, which is less than 1. Hence, by the ratio test, the series is absolutely convergent. Again, I hope you're not confused here on the terminology, absolute convergence or convergent. Remember, absolute convergent implies convergent. By definition, summation of an is absolutely convergent if summation of absolute value of an is convergent. So here, where an and absolute value of an is not the same thing because we have negative terms, basically we checked this by the ratio test. So the ratio test gave me this, and the absolute convergence test gives me also that summation of an convergent, right? Because it's a unidirectional statement. If it's absolutely convergent, then it is convergent as well. So when you prove absolute convergence, there is nothing else to check. The original series converges as well. Now, of course, if the series with positive terms, the difference between absolutely convergent and convergent is non-existent, essentially. It's the same series because we don't have negative terms that disappear when you take absolute values. So that's why it's kind of a misnomer to talk about absolute convergence when you have a series with positive terms. Like you don't say anything new, in other words. So we have 7 problems listed, but I think I'm going to actually add another one. So I'm going to save number 7 for later, because I just realized I need actually another example just to compare. So write an example here called number 8, and it'll be very similar to 7. So summation from 1 to infinity minus 1 to the n plus 1 over, let's say, n to the power 3. And these are the trickiest examples when the ratio test doesn't work. So pay attention here. Because n plus 1 over n third, because these are polynomials, ratio test fails. Okay, so then you could still check for absolute convergence just by looking at other tests. But now you have to take the original series with absolute values of those terms, which gives you the series with the positive terms n plus 1 over n third, and now figure out the convergence of this new series by other tests that you can find at your disposal. Now, from this point on, it's important to keep in mind what you're looking at now. It's not the original series, it's the one with the absolute values. And we check to see if it's convergent, because if it is, then we have absolute convergence, which implies convergence on the original one. So here we cannot use ratio test, but we can use the limit comparison test with the series made of the dominating terms, which is 1 over n squared. So now I'm going to apply the limit comparison test. So I'm going to take the limit of n plus 1 over n third divided by 1 over n squared. So that essentially means limit as n goes to infinity, n plus 1 times n squared over n third. N third plus n over n third. Dominating terms are the same. The limit is 1, which is a positive limit. What does the limit comparison test says? It says that the series that I have in the beginning is the same as the series I picked, 1 over n squared. Because summation of 1 over n squared is a p series with p greater than 1, p equals 2, that p series is convergent, and that means the summation of n plus 1 over n third is convergent. Hence, the summation of minus 1 to the n plus 1 over n third, the original one, is absolutely convergent, and we are done. All right, so after you write this down and observe it for a moment, let's notice how many tests actually are here used in this short proof. Okay, so we have the series to begin with. We checked for absolute convergence, can't use the ratio test. So I take the series with positive terms by applying the absolute value. Now, what I get is eligible for the limit comparison test. So I compare it with summation of 1 over n squared. I take the limit required by the limit comparison test. I verify that that limit is positive. Limit comparison test states that summation of 1 over n squared and summation of n plus 1 over n third converge or diverge together. Summation of 1 over n squared is a p series with p greater than 1. It converges. So I have convergence for the series with positive terms, which means the original one is absolutely convergent. So we are done. All right, so now compare this with a very similar problem 7, which is summation from 1 to infinity minus 1 to the n plus 1 over n squared. Again, ratio test fails. So we're going to follow the same procedure essentially. So we take the series with positive terms, we apply the absolute value, and we get this. We use limit comparison test with the series made of the dominating terms, which is summation of 1 over n. We verify that the limit comparison test works by taking the limit of n plus 1 over n squared divided by 1 over n, which is the same as times n over 1. The limit is 1, positive number. Limit comparison test works. And now we say summation of 1 over n diverges, because it's a p series test with p greater, I should say here less than or equal to 1. I wonder if I said the other way around, because if it's less than or equal to 1 is divergent. Yeah, I think I'll make a correction later. So less than or equal to 1, so it's divergent. Therefore, summation of n plus 1 over n squared divergent as well. But we are still not done with the whole problem, because we still don't know what happens to the original one. The absolute convergence test cannot be used. It's only in one direction, right? All we concluded here is that this series is not absolutely convergent. That's all we concluded for now. We still have to go back to the original series and see if it's convergent or not. And at this point, the only thing at our disposal is the alternative series test, in which you look at the n plus 1 over n squared, you know, the piece without the negative, and check to see if it goes to 0. Yes. Check to see if it's decreasing. Yes. If it's not clear if it's decreasing, you can even use calculus actually. If you know, n over n squared is 1 over n plus 1 over n squared, you could actually differentiate this with, in terms of n, and you know, realize that it's a negative derivative. So if it's easy to spot if it's decreasing, you don't have to write a formal proof. Just check to see if it's decreasing, and if it's obvious, just write it's decreasing. So that means it satisfies both conditions on the alternate series test, which means the original one is convergent again, but not absolutely convergent. And remember, we have a different word for this. It's conditionally convergent. So we will have maybe more examples like that. We will see more examples in the next lessons. And you go again over this example if it needs to. The tedious part is always the fact that you got to make sure to conclude only exactly what the test says and not more. And I think that's it for today.